Moving on to network terminology. There's a couple kinds of packet routing, two primary types of packet routing. One of them is called store and forward switching. It predates computers. It dates back to the days of point-to-point teleprinter equipment when there was a human being that would type a message into a teleprinter equipment and it would be transmitted across some wires to a receiver where it would be printed out, and at the receiving station a human being would read it and see where it was intended to go and go over to a specific console and type the message and send it on its way. I think I have a picture of the old teleprinter machines here. So it's a typewriter. The message was sent from point to point and human beings were in the middle doing the forwarding. So it would, like, the message would be transmitted in whole and then get sent to the next point to point. In some cases it was stored on punched paper tape. I remember one of the first jobs I had, I worked at a machine company and there were CNC controlled lathes and mills and so forth, and the programmer that wrote the program for the CNC machine would punch the program onto these paper tapes or nylon tapes that were about 3 centimeters in width, and he would punch that out on a machine in the engineering office, and then he would carry it down to the floor and feed it to into the actual milling machine, and then the milling machine would start up that job and mill the material. Like I said, so the humans read the address and then forwarded it onto the recipient. In modern use, it means an entire packet is received, and these reliable transports, TCP/IP and so forth, have a notion of an ACNAC protocol, and the packet is covered with a cyclic redundancy check. So the entire packet is received. Generally, it's hardware that checks that CRC, says this is good, I've got this whole packet, it's good to go. The hardware looks at the header information that has the destination address and decides which outbound switch port it needs to send it to. This can be used in delay-tolerant applications or where intermittent communication is acceptable. In my opinion, it's not terribly applicable in real-time systems, and there's a better way from a latency standpoint. And that is called cut-through switching. And in cut-through switching, the beginning of the packet is being received, and the hardware looks at the address and looks up in a table the routing information and decides which outbound port it needs to be routed to, and starts the transmission out that port before the CRC value is received. That's at the end of the packet. And it achieves a much lower latency. So if the CRC check at the end fails, there has to be a mechanism, and all these protocols have some mechanism of poisoning or marking. There's different terminology that's used, but the last handful of symbols at the end of the packet have to be marked bad in some way so that the receiver at the other end of it, even though they started to receive it, realizes that when that end set of symbols gets there that packet was in error, and they may generate a NAC back to the sender, and the sender then can retransmit it. But it's a big boon, a big help, a big assistant in reducing overall system latency. And as such, applicable to real-time systems where you're concerned about latency. DPI is a term that means deep packet inspection. I'm not an expert on this, but I know I have at least enough understanding to grasp that it's not a cursory look. There's dedicated pieces of hardware that can perform deep packet inspection, as we'll see in some of the upcoming little short videos here. But it means taking a look inside what's inside the packets. TCP/IP network layer model has a series of layers. The layer 1 is what's referred to as the network access layer, and this layer defines how data is physically sent. Layer 2 is the internet layer, and it packs data into packets known as datagrams and contains the source and the destination IP addresses. And this layer in the protocol is responsible for doing the routing, making sure that the packet gets to its destination. The transport layer enables devices at the source and the destination to carry on a conversation, and it defines a level of service and connection status. Are we talking? Are we not talking? We can get into what quality of service means and all that, but I think that's a little beyond where I want to go. Layer 4, application layer. This provides the APIs and the protocols application program. So you're going to write an application program that wants to use TCP/IP, a set of APIs for building packets and sending them out an Ethernet connection port or some outbound port. MIMO, multiple input, multiple output. Yep. M2M, machine to machine. And in this class, I think I alluded to in the first class, when we see that in this class, this is non-TCP/IP communication. So it's some other protocol, but not TCP/IP. And an example in there, Bluetooth. IoT or IIoT, this uses TCP/IP based communication. How many are familiar with the OSI model layer of communications? You probably all, at least if you've had a networking course, you've seen this before. So this is old news. This has been around for a long, long time, and many protocols have been built that will pick or combine layers from the OSI model, depending on what the goals of the particular protocol, the application, or the solution the group is interested in solving. So in TCP/IP, they have the network access layer, and then the internet layer, and the transport layer, and the application layer. So you can see how these layers that I listed previously map to the OSI layer model, just for reference. Network topologies. There's a physical topology, and that refers to the cabling or wireless connections, the node locations, the interconnections between nodes. The physical topology is driven by the level of control or fault tolerance and costs that are required. Logical topology refers to the way the data is passed through a network from one node to another. Got some examples from our good friend Wikipedia here. Here's a star topology. No more explanation is needed there. Rings were very popular when I first started working in chip design back in the mid-'80s. We used Mentor Workstation, and they ran on what was called token ring. There was a notion of an outbound port on the workstation and an inbound port, so a packet would come into a workstation, and hardware and software in there would look at the packet and see if the packet was for this at its destination yet, and if not, it would send it on its way. And then there's mesh or partial meshes, full mesh networks, and we'll see some of that coming up. And this is becoming very popular in the industrial space because of its inherent fault tolerance. We'll see more on that coming up. Trimble Engineering is also doing some cool things with mesh networking out in the field. Token ring is physically a star topology, but operates as a ring. Most of our homes and Wi-Fi networks are physically and logically a star, right? We've got a router, and then we hook all our stuff up. I think I listed them here. So we've got a hub, a router, a gateway. Cell phones are hooked up, our computers are hooked up, all kinds of devices are hooked up, a refrigerator's hooked up, microwave is hooked up, Xbox is hooked up, got all these devices hooked up in a star topology. This next drawing is important. You'll see it on an exam, be able to draw this picture. I've had a number of meetings with engineers from Aero that deploy industrial Internet of Things, and we went out for lunch one day, and I said, what do the students need to come away with? In terms of what the overall hardware structure of a IIoT system looks like? And he whipped out this drawing and said, here, your students need to learn this. So I recreated it here. So we have a bunch of sensors and actuators communicating by some protocol, machine to machine, on TCP/IP, and then go to a gateway. So think of this as potentially a single board computer that communicates with these sensors and actuators wirelessly, okay? So there would be a CPU, there'd be memory, and it could be a whole bunch of these. In the case of the power plant, we saw that there were 15,000, just in Unit 3 at that power plant, there were 15,000 sensors. So there's a number of gateways that enable these sensors to connect towards the data center. At this point, the communication switches from machine to machine and becomes TCP IP. So we're talking IoT at this point here, or IIoT. These gateways can talk to other gateways. This might be a wired connection or a wireless connection. I showed it as a wireless connection. It's expensive to run cables. Everywhere in a deployment where you can communicate wirelessly, you're going to save cost. And cost is important for the bottom line of a business. These are rapidly becoming wireless communication. This could be wireless as well. Eventually these gateways, one or more of these gateways ties into the in-house network either wirelessly or by a hard Ethernet cable. And the in-house network provides access to storage and servers and the daily driver computers of the employees at the business. That then, think about back to the picture of the platform. So part of the platform view, the software view, is here is wirelessly communicating to cloud and fog services where additional servers and storage are made available. And the last piece is cell service providers allow us with our cell phones to communicate to the cloud service providers to check up on what's going on, look at data analytics runs, also communicate with the factory or the physical plant, cyber physical system, find out what's going on there. So we've got this sort of three-way communication thing taking place. And this was the picture that he drew and he wanted you to be able to take away. So you go to a job interview, important to understand these terminologies and this topology.